Hi everyone. So for today's video, I'm going to be going over the first couple of reactions that are going to be tested over in exam 3 on the final. And I'm just going to essentially be showing you guys the mechanisms, and I'll be going over pages 1 and 2 of the reaction sheet that everyone should eventually have and have printed out. So I'll be showing the mechanism and kind of the concepts of these reactions that explain why these things happen, and essentially allow you to understand, what we're doing in these reactions rather than simply memorizing them, which I think is the worst way to go about doing these reactions. So if you have your reaction sheet, right? You should see on the first page something that looks like this, right? And so these are the first two reactions. And what we see over here are a couple things. We see the way this reaction sheet is set up. It's a very helpful reaction sheet. Background on the reaction sheet. It'll essentially give all the types of reactions that you need to know for the tests. And there might be like one or two that are not on here that she does go over, and I'll try to hit on those and remember which ones she adds that are not on here. Essentially, this is like a very good thing to use to study for your exam 3. It gives you some notes about like kind of the concepts and things that can be used, and then they give you some kind of details about like how the addition works, and we'll talk about these terms, mark and anti-mark, and things like that. So if we look over here, we have essentially what we're doing now for this test is we're going to be doing more double bond synthesis. We're going to be doing double bond or alkene reactions. We're going to be doing alkyne reactions. We're going to be doing things with alcohols. We're going to be doing oxidation, reduction reactions. We're going to be talking more about electrophiles and nucleophiles and just things of that nature. And mainly just we're going into our newer functional groups, double bonds and triple bonds and alcohols. We're going to do some things with carbonyls, and we're going to be showing reactions that we can do with those things. And so that's essentially what we're doing. So we're starting off by doing two double bond reactions. So here we have a double bond and we have a reagent, right? So the reaction shows that when you use this in the presence of double bond, so we have an acid, right? HX, so HCl, HBr, HF. We can promote the formation of a Mark substituted halide substituted double bond. So what Mark means essentially is addition of the substitution molecule, right? The halide and the most substituted carbon position. So Mark means adding the halide in the position that is most substituted. So right here, this is a carbon that has 2 other carbons on it, right? So this is the secondary carbon versus over here is only a primary carbon, right? There are no other carbons aside from this one right here that are next to it. So this is what Mark means. Mark means most sub addition, right? And if we were to understand how this reaction works, it'll make a lot of sense rather than having to just simply memorize how this works. So if we have a double bond, right? I have these hydrogens, right? I have a CH3. I have a hydrogen, okay? And essentially what we're going to learn now is that double bonds can be nucleophilic, right? They are electron dense, and the atoms that own the double bond, one of the carbons, can take ownership over those electrons and behave nucleophilically and form a bond with an electrophile. So an electrophile is something that is partially positive or positive and is electron deficient. Nucleophiles are electron dense. So here I have an electron dense region, and then I present the environment with an acid. So let's say I use HCl, right? And we all know acids are acidic because we have the creation of partially positive hydrogens that makes them acidic. and therefore they're very receptive to be, taken away by things that are or things that are electron dense, like bases. Bases and nucleophiles are very similar, right? So the chlorine is pulling on the bond between the hydrogen and itself, and it wants to take ownership over those electrons. That makes the the hydrogen partially positive. This is partially negative, right? So the double bond is going to come and attack this hydrogen, and the chlorine will get that pair of electrons. And when we form the first product of this reaction, what's happening is we have to decide which carbon is going to be taking ownership of that bond. So what I mean is, which carbon here is going to be the one that forms a bond and which one is now going to be deficient. So now we're going to create an unequal separation of those electrons. So one carbon is going to form a bond, it's going to be octet, and the other one is going to be missing a pair of electrons. So we have to decide which carbon, so this carbon or the other one, that's going to be positive essentially, right? So one of them is going to get a hydrogen, the other one's going to get a positive charge. And if I remember, when I talk about carbons with positive charges, in terms of stability, I prefer tertiary over secondary, right? So that means I want to form the product, stability-wise, the major product is going to be the one that forms a carbocation on the secondary or tertiary carbon as my intermediate. So my first product is going to be this carbon right here on the left is going to be the one that gets the hydrogen. So over here I have H, 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 and then on this side, right, I'm going to have a positive charge. So I have the H and the CH3. And then what happens at this point is the Cl minus that I just created, right, is now a nucleophile, and it can come and attack this site right here, right? Although it's not a strong nucleophile, right? Leading groups, right? Chlorine, bromine, fluorine, iodine, they're all leading groups. They're good leading groups because they're very electronegative, and when they become negatively charged, they're pretty stable, right? So they're not really nucleophilic, but this is kind of like SN1, where whenever I form a positive charge, it allows weak nucleophiles to come and substitute, even though they wouldn't normally have otherwise. So it's kind of like that. So I have a positive charge created, and I have an environment where I'm creating lots of Cl minuses, and the Cl minus is now going to act nucleophilically, and it's going to attack the electrophile right here, which is going to be this carbocation. So this is going to come, and I'm going to get these hydrogens, and I'm going to get the chlorine. Don't worry about me switching the places of the CH3 and H. It does not matter. Okay. And essentially what we see is now I've formed the most substituted chlorine substitution on this molecule. So this is what we call Mark. Okay. And Mark always happens because this is always going to be forming the more stable carbocation intermediate, and that's why we get Mark. Okay, all because of the carbocation stability that allows the next step of the reaction to perform. And that's the same reasoning behind SN1, where we need tertiary and secondary leaving groups for SN1 to progress, because we need the formation of stable carbocation intermediates. Otherwise, the reaction won't progress, right? And our weak nucleophile will not ever be able to substitute. So this is essentially very SN1-like. Okay. Now let's look at the next one. We have addition of HX, which we call anti-mark. And the reason we call it anti-mark is because when we have the addition of what we have over here is ROOR. And what this is a peroxide. So a peroxide is anything that's essentially like this. Okay, they look like this. So O, and then something, right? So R means any general R chain, and we have this. So these are two common peroxides, right? It could be CH3OOR, CH3OO, CH3, anything like that. So what's special about peroxides is that they undergo homolytic cleavage in the presence of heat, or usually heat promotes it to form. But if you know from your biology or whatever you're taking, peroxide formations are actually very dangerous and toxic to our cell environments, because they form these radicals which are extremely reactive in the cell environment. So peroxides are extremely toxic to us. Okay, and so essentially what happens that's different over here is that we have the formation of radicals in this environment, and that changes everything. So let's say I have the same double bond, right? Okay. And before I have this first step, what's happening is I have these R, O, O, R, right? And let's say like I have heat, okay? And what's happening is I'm having homolytic cleavage, okay? So I'm forming this. Okay, this is off in the background. And I'm forming OR, and I have a radical right here. And I'm forming, there's two of these. And what happens with this is that this is going to react more reactively with our acid than the double bond will. And so what's going to happen is I'm going to have my HX, right? I'm just going to put HBr, and I'm going to have a half reaction, right? And what's going to form is I'm going to get an HOR plus halogen radicals. So I'm going to get halogen radicals, and this is going to now react with our double bond. So my halogen radical is going to come, so I'm just going to draw it over here, right? And I have my radical, and I'm going to have a half reaction. Okay? And I'm going to start writing in a different color because it might be kind of hard to see where I'm going. So I'm going to have a half reaction. Okay? And now I have to remember the same rules apply, right? It's just different things. So before, I had a reaction with an acid, and one of the carbons in the double bond got the hydrogen, got the bond, it was stable, has octet, and the other one loses out, right? So one carbon is always going to lose out on an electron when I do these reactions in the double bond, right? So what I have to think is, the first one, I form a positive charge. Over here, I have a half reaction. I'm forming a radical on one of the carbons. So which carbon am I forming the radical on, right? So one carbon is going to get the Br, other one's going to get the radical. So the one that's going to get the radical is the most substituted one. Let me draw the arrow like this over here, just so everyone sees. It's not like two of the different line, the bonds that are reacting here. It's the same one. So what I'm going to get is I'm going to get the double, no longer a double bond, right? So I'm going to have this, okay? And I'm going to have the hydrogen, and now I bonded the bromine with this carbon on the left. So I have the bromine over here. And then over here, right, is where I have my CH3. And I have a hydrogen, okay? And I have a radical here now. So now I have a radical over here, and what this happens now is this is going to now react with the HBr again, right? There's plenty of these in concentration in the reaction. So there's like millions of these floating around. So there's plenty for this reaction to keep progressing. And this is going to be a propagating reaction, right? Just like we've seen in the first exam of this material. So what's going to happen, I'm going to have a half reaction over here. I'm going to add a hydrogen, and I'm going to form more Br radicals. So this is going to propagate, and it's going to react with more double bonds, etc., right? But the main thing is I get my product, and my product is going to be this Br, hydrogen, hydrogen, right? And I have hydrogen, hydrogen, CH3. Okay, so what we'll notice now is that I have my primary halide addition, and my secondary is now not where the halide addition was. In my first reaction, the Mark one, I had the secondary halide addition location, so substitution there. And the reason for this is because I've introduced the peroxide over here, and this changes from Mark addition to anti-Mark. Okay, so anti-Mark means that I have a least substituted carbon addition of the halide or whatever group that's being added in the reaction, right? So, and this is due to the peroxide. Okay, so peroxides will always change the reaction from being Mark to anti-Mark. That's something important to remember. All right, let's look at some more reactions. Not too bad so far. Okay, now if we move on, something a little bit different. So these are the next two. All right, and I hope everyone is like with me with the reaction sheet and looking at this. So in this reaction over here, what we're doing is we are adding a halide. So either Cl2, Br2, F2, those types of what's it called? We have is these dihalides, so dibromide, dichloride, those kind of things, right? And what we're doing is we're adding both of them, right, on the double bond. So each carbon of the double bond is going to be substituted with one of those halides, right? And anyone could just go look at this and be like, okay, Br2 or Cl2, and I just add two of them, easy peasy, right? And we have other factors we have to consider, the anticoplanar. So someone may just go and memorize these things and just know I have to draw them on opposite wedge and dash, and I just add them to each one of the carbons. But I think it's much more educational if you understand how they become anticoplanar and how this works. So essentially, what happens is I have my double bond, right? There's no stereochemistry on a double bond, okay? Double bond groups. And D just means deuterium. So whoever made this reaction sheet likes to use deuterium occasionally. I guess just to be a little bit more, I don't know, unique than a hydrogen, but it doesn't really matter. Could have been a hydrogen there. And this reaction progresses in the presence of, let's say, Br2, right? So I have this Br2 over here. And essentially what happens is, okay, so this Br2 is electrophilic, and to kind of understand that is there's going to be an unequal sharing of the bond between them. So one is going to have more ownership over those electrons than the other, so causing one to be more electrophilic than the other, and one to be to have more ownership, so I guess more nucleophilic, right? So we're going to have like partially positive and partially negative division over here. And so it's arbitrary. They're all like, you know, there's no way to like say which one is which, but one is going to be partially positive, one to be partially negative. And essentially in the presence of electron dense regions or nucleophiles, right, the Br2 can be susceptible to nucleophilic attack. So what happens here is the Br is going to get attacked, and when it gets attacked, this group leaves, right? And we also form a positive charge at the same time. So the double bond breaks, and the Br is grabbed, and as it's grabbed, it also simultaneously attacks the site that loses the bond. So you could have done this the opposite way. You could have made this carbon the one that grabs the Br and this one the forming the positive charge, right? And this happens very quickly. So what happens is the double bond breaks and Br gets grabbed, and as it's getting grabbed, this bond breaks and the other Br takes the pair of electrons, and the Br itself that was grabbed with one of its pairs of electrons attacks the carbocation that forms. So essentially what we get is, right, so I'm just going to draw it out. We get this kind of weird structure where I have the Br that's attached to both the carbons and that were part of the double bond like this. So the Br came, was attacked, then attacks at the same time. And I get this kind of in the same plane with the same wedges and dashes attachment to the Br, and then you have the other groups out on the same plane, right? So this is how you would write it. And I could have also written out with the Br on light wedges and the other groups on dark, right? It doesn't matter. It's up to you. But we have to be consistent, and it just depends on how you choose to make what's dark wedge or what's on light. And so at this point, what happens is we're going to have the Br minus that formed come and it's going to come and attack back, right? Because this is not very stable, right? I have the Br, it's sharing bonds with two sides, right? And it's right, and so this Br is actually positive over here, right? If you count the formal charges, and because it's positive, it's now susceptible to, it's going to be pulling on these bonds much more, right? Because bromine is electronegative, and so therefore it's going to be pulling on the bonds that it's sharing with the carbons, and those sites are now going to be susceptible to being attacked by the Br minus. And so essentially what happens is the Br minus is going to come and attack one of these sites. Okay, so now these carbons over here are going to both be partially positive. So the top one and the bottom one are now partially positive. And so the Br doesn't matter which one you attack over here because you will still get the right answer regardless. But I believe the Br will come and attack from the more substituted side. And when it does that, these electrons go back onto the Br, and the Br now becomes stable, and I have an addition of the other halide. So when this happens, it's very SN2-like, and it causes the stereochemistry on the side that gets attacked to flip. And so on the top side, right, that gets attacked, we have a flip from CH3 being on light wedge to being on the dark wedge, and I have the bromine now on light, and then on the bottom retains its stereochemistry. So now I have over here Br like that on dark, and the deuterium on light wedge as it was. And this is how we get the anti-coplanar attachment of halides on double bonds. Okay, so the only difference between this one and the one underneath it is essentially we have it in the presence of water, right? And the only difference really is that it's the same thing, right? So the first step happens the very same way. So we form the this again, right? But the difference now is at this step, what happens is instead of having the other Br minus attack, water is going to be attacking here. And water will attack over here, right? And I'll get this be pushed off. And then get this. So this is Br minus. Always show the charges. And right? So we have the OH2 coming and attacking over here on the more substituted carbon. And the reason why we attack the more substituted carbon is because this carbon is more stabilized than the other ones, and therefore it's able to be more partially positive and give away more of its electrons than the least substituted carbon can, right? So whenever this positive Br is pulling on these bonds and making these carbons partially positive, the more substituted carbon is able to stabilize itself by the other carbons that are around it, right? So therefore it can give more away, more of itself, of that bond can be taken away compared to the substituted carbon that can't so easily have so much of its bond, sigma bond, being pulled away. So this is why we attack the most substituted carbon over here, right? So when this happens, right, the OH is going to flip the stereochemistry on this side, so I get the CH3 like this, and I get my OH 2 like this. And now I'm at my deuterium on the dash, and then the Br on the wedge. And essentially what we want to take away from this is that now I'm not done yet. I have OH2, and this gets deprotonated, right? So another H2O comes, or the Br minus comes, and it deprotonates this OH2, right? And now I no longer have the OH2, I have OH, right? So I form the alcohol product, right? And so at this point, what we want to recognize is that I have substituted the alcohol, right, the OH, on the more substituted carbon over here. So this is the tertiary carbon, and this is the secondary carbon. And so what we want to remember about this reaction over here, that it is Mark. So we have the Mark addition of the H2O as well as the halide on this molecule. So we have OH addition on the more substituted carbon and the Br substitution on the least substituted carbon. And this will give us our product over here. Okay, so that makes sense, right? So the anti-coplanar orientation of the groups that are substituted makes sense now, and the Mark component of addition makes sense, right? And so those are those two reactions. All right, moving on. Now let's kind of backtrack a little bit, and let's look at another way of forming alkenes, right? So we'll learn some new ways to form alkenes besides E1 and E2. And this is very E2-like reaction. And if you look over here, it's like forming alkene from the vicinal dihalide. Okay, so we know how to form the dihalides, right? But not necessarily whether they will be vicinal or not. But you won't really ever have to form like the dihalide and then do the NaI or Ki reaction. So what happens here is we have this vicinal dihalide, and what happens is the I minus, right? So Na is just the spectator ion. The I minus attacks one of the bromines, and this bromine's bond is broken and is used to form a double bond, and the other bromine now is a leaving group and it leaves, and then we get the formation of the double bond, right? And the same thing as before, whenever we do E2, the anti-coplanar rule, which they are an anti-coplanar right now, right? So it's very E2-like, and the wedges go on the same side of the double bond, and the dashes go on the same side of the double bond. So I have the H and the H on the same side, or in this example, and the CH3 and the CH3 on the same side. I wouldn't worry too much about you know, how this works, right? But the iodine associates with the Br, and it forms the IBr, and the Br group breaks this bond, forms a double bond, and then this Br minus leaves, and then we get a double bond formation. Okay, and it's very E2-like because they have to be in the anti-coplanar formation. Okay, so in this reaction sheet, there are quite a few reactions that you can really understand, and then some of them you don't need to worry about too much about understanding it fully. But this is a good level of understanding that what's happening here, essentially. Okay. Now let's do two more that are more useful to understand, and that we will be using a lot more commonly in synthesis and in the reactions and the mechanism. So over here we have dehydration of alcohols to form alkenes, right? And dehydration is just essentially the removal of alcohol groups in the form of water, usually, and them becoming alkenes as a result. So this is a very common reaction in nature, and essentially whenever we say dehydration, we usually mean double bond formation. So, and when we say hydration, we mean removal of double bond to and addition of an alcohol group. Okay, so now let's look at these two reactions and let's look at the differences between them and why they're different. So in the first one, these are both, let's just notice one thing, okay? We're both looking at primary alcohols, okay? That's important in terms of understanding stability reasons. And so I have these primary alcohols, and I'm using them with different reagents. I'm using H2SO4, which is a very strong acid and heat, and the other one I'm using POCl3 and heat, okay? And the first one, it says it's E1-like and it cannot give the terminal alkene, and then the second one, it says dehydrates to form a terminal alkene. So one, H2SO4 forms a terminal alkene, forms the internal alkene, aka the most substituted one, and then POCl3 is able to form the terminal one. So these are important and when we want to form different types of double bonds, right? And let's say we don't have a leaving group and we're not able to, use a base to promote E2 or E1 or things like that, right? And it's also very interesting because normally when I have a primary leaving group and I want to form a double bond, I usually can't, right? I have to have tertiary or secondary when I'm doing E1 and E2, right? And if I am doing if I have a primary leaving group and I have a strong base, it usually forms SN2 as the major product and not the double bond product, right? So these are ways that we can get the terminal alkene and a double bond from whenever we're looking at primary carbons, okay? But it has specifically primary alcohol. So what happens essentially is I have this carbon chain, okay, and I have this alcohol group over here. And if you understand, the basic acid-base chemistry, right? This alcohol group over here is a much weaker acid than H2SO4. So that means in the opposite, that OH is going to be a stronger base than H2SO4 is, right? So OH is going to deprotonate H2SO4 with its pair of electrons that it has, and H2O4 is going to be deprotonated and we're going to get the conjugate base, right? And so what happens is H2SO4 looks like this. So I have H, right, and I have SO3, right? I have, sorry, I drew that wrong. So it's H bonded to an O, and then this is bonded to the S, O3H. H2SO4 looks like this. I have a sulfur, has two carbonyls, right? Not really carbonyls, but they are the double bonded O's. And then I have OH, OH, right? And these are acidic hydrogens right here, right? Because how stable this structure is once I deprotonate and I form a negative charge, right? The strength of an acid is determined by how stable the conjugate base is. So here, this is a very strong acid, and the OH with one of its pairs of electrons comes and takes the hydrogen and deprotonates the SO3, the H2SO4. And what I get is essentially a good leaving group, right? And I have this H2O plus now, right? Okay, so now I have this good leaving group, right? The oxygen is positive, and therefore it's pulling on this this carbon's bond right here, making this partially positive, right? And essentially, what this does, this makes these hydrogens acidic over here, right? And um, and this is very specific because we're doing this in the environment of SO3 um, SO3H minus, which is not a good nucleophile because it's very stabilized. So we don't have a SN1, SN2 like substitution here. We're going to be forming the double bond and getting rid of this OH2 group. And normally what would happen, right, especially on primary carbons, is primary carbons are not stable enough for this to just leave like this. And normally what would happen is one of these H's would be deprotonated, right, be taken away by the it can be SO3H, right? It can be that, but it's more likely to be what is going to be found in solution is water, right? Water is usually always in solution. These are usually very what we call aqueous solutions. So that means there's water present in the solution. So water will come and it will take one of these hydrogens and form the double bond, and this will be kicked off to force us to leave because it couldn't leave otherwise because it's primary, right? And normally this would form the terminal alkene, right? But what happens in this situation is we have carbocation rearrangement, and essentially we have a hydride shift that allows the movement of the positive charge to a different carbon and allowing us to form the more substituted double bond. So this group is going to leave, right? And what we're going to form this, and very quickly we're going to have a hydride shift that changes the position of the carbocation from a primary to a more stable secondary carbon. And then at this point, right, we can take one of the adjacent hydrogens and form the internal or more substituted double bond here. So we're going to bring water again, right? And this has to be in the presence of heat. Heat helps promote dehydration always, and it really helps in this case the formation of the more substituted double bond, right? And at this point, I form the internal alkene. Okay, so know that in this case, I always form the more substituted double bond when I'm using H2SO4 and heat, and that's really all you need to know, right? You won't be really tested too much on this kind of mechanism right here. Now, in the case of POCl3, it's a little bit different, right? It behaves differently, and this will be easier to understand if we look at what POCl3 really looks like. And what it looks like essentially is this. So we have this phosphorus, and it has a double bond to the oxygen, and I have a bond to a chlorine, a bond to a chlorine, a bond to a chlorine. And essentially, this site right here, the phosphorus, is extremely electrophilic. And I have electron density going in this direction, this direction, this direction, right? Because these chlorines are electronegative. And essentially making this phosphorus very partially positive. And because of that, the oxygen now, with one of its lone pairs, is more nucleophilic, and it attacks the phosphorus right here. And what we form, okay, so bear with me. So I have 1, 2, 3, and I have the oxygen, and now it's bonded to the phosphorus, right? And okay, so now it's bonded to the phosphorus, and what happens is this attacks from over here, it attacks the phosphorus over here, and it pushes up one of the bonds in this carbonyl-like structure, and we form an O- up over here. And this is kind of higher level concepts, but it will help you later on in the more complex reactions to come. So I have these groups, right? And I have a negative charge. And what will happen now is the molecule will now gain stability internally rather than going outwards and stabilizing itself by doing an acid-base reaction. So it's more stable for this to regain the formation of that carbonyl structure. So what will happen is this pair of electrons will come back down, right? And because we have a leaving group over here, this will allow this to occur. So it's more stable for this to reform the double bond and kick off one of the chlorines rather than abstracting a proton and forming an OH group, right? And so this will form now, okay, the O, right, bonded to the phosphorus now with the two chlorines coming out like that. Right, I kicked off one of the other chlorines. So now I'm left with two. And don't forget that we have the hydrogen over here. Okay, so I have that hydrogen over here. I have a positive charge. I forgot that. So I have the hydrogen over here. I have a positive charge. And at this point, right, it's a complicated mechanism, but essentially I'm just showing you how we're able to form the more substituted the least substituted double bond in this case, and why it differs from H2SO4 and using POCl3 heat forms something completely different. So I'm gonna erase everything and I'm gonna continue this on a new page, right? So I'm going to copy and paste that, bring this back up here. And so the step that we're at right now, we have the oxygen, right, with the hydrogen, and it's bonded to the phosphorus that now has the double bond again with the O and two chlorines. Okay, and at this point we're going towards stability. So I'm going to stabilize this molecule before anything else can happen and before I can do any elimination, right? Before I abstract any other hydrogens on this molecule, which are not as acidic as this hydrogen right here. So again, we're going to use the water, right? Or we can use Cl-, and we're going to take this hydrogen and we're going to give this oxygen back its pair of electrons. Okay. Again, this mechanism is not that important, but I always think it's beneficial, and I learned a lot on my own by finding out these mechanisms, and I learned a lot from just how these things happen and when they happen and why it happens, right? And how this helps form the different products that we have. So now I have this structure over here, right? And if you remember from our drawing of SO3H, right? The reason why this is still stable, right, and why it's such a good acid is because I have this resonance. It's resonance stabilized, right? I can have resonance over here, and I can either go up in this direction or I can go over in this direction. So I have three resonance structures, right? I can resonate the negative charge onto 3 different oxygens. And it's very similar over here, right? I have a resonance, potentially resonance stabilized product. So, and if you look up OTOS, remember OTOS, everybody, from our SN2 strong good leaving groups? This is a good leaving group because it's resonance stabilized when it leaves. So it's very, it doesn't mind leaving with those pairs of electrons and taking on a negative charge because it can stabilize them very well. And this is the same thing here, essentially. So on this carbon over here, I have a bond to a carbon, I have a bond to this oxygen, right? And I have 2 hydrogens on this carbon. And essentially, right, not this carbon. Essentially, right, I'm looking at this carbon over here and this carbon right here, right? And essentially what happens is I'm going to be able to take one of these hydrogens, I'm going to abstract them, right? They're acidic enough, and I can form this double bond and I can kick off this leaving group, right? Because it's stable enough to leave like this. And so now I can form the terminal double bond and then the leaving group that I get is this O minus double bonded to this oxygen, and then I have the chlorines. So the chlorines are going to act inductively, first of all, right? And then I also have resonance that can resonate the oxygen negative charge between this oxygen and the other one. So I have a resonance stabilized product and inductive effect as well as on there, which allows me to form the terminal alkene in this case. So because I can have a very stable leaving group over here, it allows the double bond to form in this location. Whereas before, with H2SO4 and heat, I had to do carbocation rearrangement, aka the hydride shift or methyl shift that occurs, and other types of things that you see in mechanism to help form the more stable carbocation, and then I could have the double bond formation, right? But here, I don't have to worry about that because I have this very good leaving group that lets me form it in that location. And essentially this allows us to form the least substituted double bond. So just remember POCl3 allows us to form terminal alkenes, and H2SO4 allows us to form internal, and more specifically the most substituted double bond because they're the most stable. Okay. So these are just two ways to form double bonds from alcohols. And we will learn how to make alcohols soon, right now. And those are the next set of reactions. So in this next set of reactions, we are going to learn some alcohol additions. So let's look at one over here. Okay. So I have a double bond and in the presence of H3O plus, right? And this is a very convenient and nice way to add alcohols to the most substituted double bond, most substituted carbon in the double bond. Okay, so just remember it's Mark, right? And so I don't know why there's a CH3 group here specifically given like that, but essentially I have the double bond and I have, let's say I have one that's more substituted than the other. And what happens really is I have the H2, so it's H3O plus, right? It's acidic. And the double bond is now going to react with this. And so this is a nucleophilic and this is electrophilic region over here. And double bond is going to abstract that hydrogen, just like we saw before when we had the HBr reactions or HCl reactions or anything, any HX reaction. It works the same way. So double bonds are able to react with acids very, very well. And so I form in the double bond is removed, and just like before, I have to form the carbon, with the carbocation that's more substituted because it's more stable. And then I get my hydrogen substitution over there, right? And so at this point now, the OH2 is now nucleophilic, and it can attack with one pair of its electrons at the carbocation, so just like SN1. So it's very SN1-like, right? Where we had H2O acting as a weak nucleophile and attacking carbocations, right? And so this is very SN1-like, and we just have the substitution of water on the carbocation location. So I have the water, and then obviously it's going to be positive, so I have to deprotonate, and I get rid of one of the hydrogens, and now it's neutral. And then I have the methyl group, right? So it says over here it's racemic, and like I said, this is very SN1-like. Okay, so the water comes and attacks, and it can attack from either the top or the bottom, right? And so that gives me a mixture of wedge and dash products. So I could have, the dash product, the oxygen on dash, and the CH3 group on a wedge. Or I could have it in reverse. I can have this on the dark wedge, and this can be on the dash, right? And that will give us a racemic mixture, just like in SN1, right? Which means 50% S and 50% R, Okay, so it's a racemic mixture in this case, and this very clearly explains why. So this is just a convenient way to add to form alcohols on the more substituted carbons from double bonds. Okay, so that's just one way of doing it. Now, some other ways of doing it are going to now be visually similar, and the way the reaction works is going to be very similar to what we've seen in previous reactions, right? So, two other ways of adding alcohols to the more substituted carbon, and we can even do we can actually add formation of ethers as well as forming alcohols. So an ether is essentially a carbon attached to an oxygen attached to another carbon. So it's carbon, oxygen, carbon. That's what a ether is, right? So forming OR groups on molecules. So if we look over here, we have the formation of the more substituted double bond. And if you understand this, you will never forget whether it's mark or anti-mark and anti-coplanar and all these things, right? So this will be extremely helpful for you if you're having a hard time remembering whether it's anti-mark or mark or anti-planar or whatever. And if you understand the mechanism for these key reactions, you will never forget, and it's a lot easier to learn than just sitting there and trying to memorize over and over. So this reaction, I'm going to say, is extremely similar to the dihalide addition, right? So Br2 or Cl2 addition to a double bond. So if you remember from earlier, I'm going to remind everyone it's very similar. So go look back at your notes, and I'm going to say it's similar to this reaction right here. Okay, so it's very similar. So if you remember the mechanism for this, it will help you a lot to understand how this reaction works. So the way this works is, let's take a look at what HgOAC2 is. So this is what we call Oxymercuration-demercuration reaction. Okay, so what this HgOAC2 looks like essentially is it looks like this, right? So I'm just gonna take this from the book, and the book will show it best rather than me writing it out all ugly like. And essentially, it gives us this, right? So when we put in HgOAC2, we have this formation right here. Okay, so HgOAC2 looks like this structure right here. We have mercury attached to two oxygens, and these oxygens are both have carbonyls, right? And we have the CH3 groups over here, right? So this is what the OAC group is, the oxygen connected to the carbonyl carbon, and we have the an ER group, okay? And then what happens is we're going to have one of the oxygens break off and take the electrons away from the mercury, and we're going to be forming a positively charged mercury over here. So this is really what we're dealing with, and putting in the HgOAC2 allows me to form this, okay? And when I form this is going to be susceptible to being attacked by the double bond carbon, right? Double bond carbons. So double bond is electron dense. The Hg is now electron accepting. It's electron deficient, right? And so, right, and this is all about stability, right? This can form because this is a stable molecule here. It's resonance stabilized. So resonance stabilization is extremely important in a lot of these reactions and forming these things. So I have this Hg whatever OAC group, and double bond is now going to come and attack this Hg, right? And the Hg now, just like with the Br2, will come and attack back, right? Forming this kind of triangular bond formation that we saw before. So just like with the Br, this is going to get attacked, right? And then it's going to attack again. and then this will allow us to form that triangular type of formation from the double bond. So over here I get, let's say I put this on a dash, I'm gonna put D on a dash, and then I'm gonna put these on wedges. Right, so I have the Hg, and the Hg stays positive because first it gains electron, and then it attacks and it still loses. So there is no net gain or loss. It maintains that same positive state, and that's going to be important. Okay, so I have this Hg, and now it's positive, right? And now I have the Hg, and then it's bonded to the OAC group, right? So I'm just going to put that like that. And now what happens at this point is just as before, right? So let's say I'm looking at the first reaction, right? And I'm doing this in the presence of water, right? So I have this OH2, and just like before, the water in the presence when I had so let me get rid of this one, right? And let me bring this one right now to show you, right? So when I had this reaction from before, right, the water is going to attack now instead of the Br. It was Br before Cl, and instead of this one attacking, we have the water attacking. So the water is going to attack from the more substituted side, right? So let me actually use a red arrow, red colored pen, just so it's not confusing. So the water is going to attack from the more substituted side, just as before, and we explained that because this carbon is more partially positive than the other one, and this is going to break off this Hg group, and what we're going to get is we're going to get the ring, right? So I'm going to get stereochem flip on this side first of all. So I'm going to have the water on the on the dark wedge, right? So I have the OH2, and then on the light wedge, I'll have right, on the light wedge, I will have the CH3 group. Okay. Oh wait, no, I did this wrong. I will have on the dark wedge, I will have the CH3 group. Yes, and then on the light wedge, I will have the OH2 plus, of course. Okay, and then over here, I have the retention. So retention means retaining the stereochemistry, and I will have the Hg OAC. Okay, and now at this point, right, I have deprotonation, right? So the water gets deprotonated, and I get now, I'm just gonna erase this, right? So now I have water, I have alcohol now, and so now it's neutral, and then this is where the second step comes in. So now I would normally have my product if I didn't have my second step, and now what I have is NaBH4, and what we're going to be seeing this guy much later, but NaBH4 essentially is going to what we call, it's going to reduce. It's a reductive reagent, and so we're going to reduce this mercury over here, this carbon with the mercury attached to it, and essentially what that means is it's going to be replaced with a hydrogen bond, right? And so this mercury is going to be disappeared after this step. So I have the CH3 over here, I have my OH, and then I have my my D, and then now on my dark wedge over here, this mercury is going to be replaced by a hydrogen, and this is just a reductive step. So this NaBH4 removes the mercury, right, the HgOAC group, and it replaces it with the hydrogen. Okay, and now we get our, right, we added a hydrogen and we added the OH group, and they are in antiplanar format, right? And now we also have the OH addition on the more substituted carbon, right? So the CH3 is here, for those of you who are confused. And so I have the Mark addition and antiplanar formation of these additions, right? And essentially the only difference between this one and the next reaction, right? They're the same, is just instead of having water over here, we use an alcohol. And this works the same way. So the alcohol addition will add over here, and then I'll deprotonate, and then I'll get the OCH3 addition. So it works the very same way. Okay, so this is a way to add alcohols to the more substituted carbon on double bond, as well as adding a hydrogen on the least substituted carbon. Okay. All right, now for one more reaction of adding alcohols to double bonds is going to be called hydroboration. Okay, and this one is different and unique because it adds the alcohol to the double bond in anti-Mark formation. Okay, and it adds them as well in syn. So essentially, I wouldn't worry too much about the mechanism here. I can show the mechanism to anyone who requests it, right? But it's not all too important here in understanding how this works. It's kind of complicated a little bit and kind of lengthy. But essentially what you need to know is that what happens is the BH3 and THF complex allows the addition of a hydrogen to the more substituted carbon, and then once that product forms, H2O2OH addition in the mixture allows us to add a OH group, right, to the least substituted carbon, and those OHs and the H are going to be added in syn addition. So this is essentially all you need to know, is that you add the OH to the least substituted carbon on the double bond. And if you have a hard time remembering if this is going to be a least sub or most sub, just notice the peroxide here. And this does not work with radicals, but usually almost always whenever you see a peroxide, it indicates anti-Mark addition or least sub addition of the important functional group, which is the alcohol here. So this will be more of a memorization one. If you want to see the mechanism, I can show the mechanism, but it's not that important. Okay, so some mechanisms are important, some are not. All right, so now let's finish up the second page and let's cover these last 4 reactions. Okay, so they're not all the same, but I'm putting them all together like this because they're more memorization type of reactions. You don't really need to know the mechanism for it too, really, and you should just try to memorize them and form your mnemonics or whatever to help you figure it out. So we're going to be seeing these catalytic hydrogenation sort of reactions very frequently. So we're going to see these plutonium, palladium, or nickel combined with H2 catalytic hydrogenation. Essentially, what is happening here is we have the metal, and there are many like hydrogens on there. And what this does, it kind of comes underneath on one side of the double bond, and it attaches hydrogens in syn to that double bond. And so what you essentially do is it breaks away the double bond and replaces the double bond those carbons, that the double bond with hydrogens. So we break the double bond, replace everything with hydrogens, and essentially that's all you need to know. And it's very simple, just adding the hydrogens in syn. And so you need to be careful about the stereochemistry and make sure that you have the D and the CH3 on the same side. And one thing I would like to add actually about this is that you normally what you'll see here, I believe, is okay. Never mind. It's essentially you can write it the hydrogens up or down. I don't think it really matters, just as long as they're syn and you write them out in syn. Okay, that's the only thing that matters about this reaction. And this is a very easy memorization one. So if you see any nickel, plutonium, palladium with H2, that always mean I have catalytic hydrogenation, and just replacing all the bonds, right? You're fully saturating all the bonds in this molecule, okay? And we'll see this come up again and again in different examples with triple bonds. You'll have other ones with carbonyls and things like that will completely remove all the excess electron density areas and fully saturate everything. Okay, so this is very easy. And now let's look at some what we call glycol synthesis. And glycol essentially is the dual addition of two alcohol groups adjacent to each other. So there's three ways that we can do this. Okay, two of which, right, the first two are syn formation, right? So that means the alcohols are added in the same side. So we have them in the same wedge and dash, same wedge or the same dash. And the first one is OSO4 H2O2, and then the second one is KMNO4, and the conditions are cold and basic. Okay, so pay attention to these. And if you have a hard time with OSO4, one of my friends came up with like a really, I guess, interesting and silly way of remembering it. So oso sounds like bear. It's bear in Spanish, right? And if you remember a bear, the dumb way is just a bear has two arms, and you can remember the arms are in syn, and you can remember that you add the two OHs in syn. It's silly, but it works for a lot of people. I didn't use that, but it helped him. And you can come up with silly ways to kind of remember these things. So just remember oso is bear, and bear, his two arms are sticking out and they're on the same side. So that's kind of helpful to remember. And then KMNO4, we're going to be using KMNO4 a lot in different conditions. And KMNO4 is just an oxidative reagent, right? So this is oxidation, right? Alkene oxidation. We're replacing the double bond and we're oxidizing it. We're adding OHs, right? So we're oxidizing those carbons, right? And KMNO4 is a strong oxidizing reagent, and when we have it in the cold basic condition, it adds the OHs in syn in this way. And that's just another memorization one. You can have some sort of logic to it, or concept to it to help you, but it's pretty much mostly memorization for these three. And then the last one is oxyrain intermediate. Not really that important, but this is the anti-formation one, which is just more. I guess you always have the syn formation and anti-formation one, just like before we had, the oxymercuration, and then we had the B2H6 one, BH3 THF that allowed us to do anti. So we always have like the syn reagents, and then we have the anti reagents. And so we have two syn reagents, and then we have the anti reagents, which is CH3, CO3H, H2O, and it adds two alcohols in anti. Okay, and there's no specificity that this OH should be dark wedge or light wedge, just as long as they're anti, and that's all that matters. Okay, that's it for today. This is the first 2 pages of reactions, and after this there are, there are 8 more pages. So it gets better from here. Okay, so just keep studying those and try not to fall behind, because it's important to make sure you're on top of these, because it does go by quickly and it is overwhelming. All right, best of luck.